In this example, we have a tension test that was performed on an aluminum specimen having a diameter of 0.5 inch. So we have aluminum specimen, this one with a diameter 0.5 inch. The data is plotted in the figure below. We are looking to figure out these values. What is the modulus of elasticity? Based on the given stress strain diagram, we have a linear relationship at the beginning. This linear relationship in the elastic stage. So the slope of this linear relationship will give you the modulus of elasticity. So the modulus of elasticity E equals the slope of the linear relationship. So I can select any point on this linear relationship and divide this value of the stress by the value of the strain at this point. So looks like we have only the last point of the linear relationship. The value of the stress is 40 and the corresponding strain is 0.004. Keep in your mind the value of the stress is KSI and the value of the strain is dimensionless. So if you divide 40 divided by 0.004, the value of the Young's modulus will be 10,000 KSI. We are going to follow the same unit for the stress. Excuse me. What is the modulus of resilience? If you remember, the modulus of resilience is the area under the linear relationship, which is an area of a triangle. So the modulus of resilience will be 1/2 time the base 0.004 time the height, which is 40. So the value will be 0.5 times 0.004 times 40 equal 0.08 KSI. What is the modulus of toughness? Modulus of toughness equal the total area under the curve. So beside the area of this triangle, we need to add the area of this trapezoid, which is 40 plus 60 divided 2 times this range of strain, which is 0.1 minus 0.004. This range equal 0.096. This is the area of this trapezoid. We have another trapezoid, which is this one. So I need to add the area of this trapezoid plus the value of stress 60 plus 50 divided by 2 times this range of strain, which is 0.1. So this will represent the total area under the curve. So we have 40 plus 60 divided by 2 times 0.096 plus 60 plus 50 divide 2 times 0.1 plus 0.08. So the total area under the curve will be 10.38 KSI. Does that make sense? What is the maximum what is the maximum force be applied to the specimen during the tests? The testing. Keep in your mind the ultimate stress. The maximum stress we reached was 60 KSI. This is the highest level of stress we reached. Sigma ultimate equal 60 KSI. If you would like to figure out the maximum force, keep in your mind, this sigma ultimate equal the maximum force we can reach divided by the area, the cross-section area of the specimen. Keep in your mind the stress equal force divide area. Right now, we have everything. Stress is the maximum 60 KSI. The applied force, I don't know. Divided by the cross-section area is a circle with a diameter equal 0.5. So pi divide 4 times 0.5 square. From this equation, the only unknown is the B maximum, the maximum force. It will be by divide 4 times 0.5 square times 60. So it will be 11.8 kip. This will be the maximum force applied to the specimen during the loading. That makes sense. So this example, we are given the stress-strain curve or the stress-strain relationship, the stress-strain relationship. And from this relationship, we figured out the modulus of elasticity, the modulus of resilience, the modulus of toughness, and what is the maximum stress. I'm sorry, the maximum force applied to the specimen. In this example, we are given also stress-strain relationship for the material of BA and BC. So we have two wires, AB and BC, having original lengths of 2 feet and 3 feet. So the length of PA was the original length, 2 feet. The original length of BC equal 3 feet. And the diameters of BA 1/8 inch. And the diameter of member BC is 3/6 inch. If these wires are made of a material that has the approximate stress-strain diagram given, we need to figure out the elongations of the wires after 1,500-pound load is placed on the platform. For this platform, we have a vertical weight here hanging out equal 1,500 pounds. So to solve this problem, we have two parts. The first part is the part of engineering mechanics. We need to figure out how much forces in member or wire AB and how much force in wire BC. This is engineering mechanics part. So I have joint B with a vertical weight 1,500 pound. And we have a wire here with a force FBC. And we have another wire here with a force FBA. Keep in your mind, we are given these angles. This one is 30, and this one is 45. To figure out these forces, I'm gonna apply equilibrium equation, summation f of x equals 0. So I will have negative FBA sine 45 plus FBC sine 30 equals 0. If you apply summation f of y equals 0, I will have FBA cosine 45 plus FBC cosine 30 minus 1,500 equals 0. Then I will solve the two equations, equation number 1 and equation number 2. Keep in your mind, from equation number 1, I can say FBA will equal sine 30 divided by sine 45 FBC. Or FBA will equal sine 30 divided by sine 45 equal 0.71 FBC. So I rearranged this equation and I put FBA in one side, so everything on the other side. I found FBA equal 0.71 FBC. So let me check one more time. Sine 30 divided by sine 45 degree, 0.71. Yes. Then I will remove any FBA and put it 0.71 FBC. So I will have a 0.71 FBC. This is FBA cosine 45 plus FBC cosine 30 minus 1,500 equals 0. The only unknown in this equation is the value of FBC. So I can figure it out. So the value of FBC will equal 1098.1 pound. So the value of FAB will equal 779.6 pound. So the force in member AB equal 779.6, and the force in wire BC equal 1098.1 pound. This is the first step in the book. The second step is the engineering mechanics step. I'm sorry, mechanics of material step. For member AB or wire AB, the applied force in this wire FAB was 779.6 pound. The diameter of wire AB, the diameter of this wire AB was 1/8 inch. So I can figure out the stress in the wire AB equal the applied force in wire AB divided by the area of wire AB. The applied force from engineering mechanics was 779.6 pound divided by pi divide 4 times diameter 1/8 square. So this stress will be pi divide 4 times 1/8 square, and this force it will be 63527.5 pound per square inch or PSI. If you would like to convert it to KSI, I will divide it by 1000. It will be 63.5 KSI. That makes sense? So if you look to the stress strain relationship given, and for the stress equal 63.5, from 63.5 looks like here, I can go to the diagram or the relationship to figure out the corresponding strain. So at this stress 63.5 KSI, the stress in the member or the wire AB. So what is the corresponding strain? How can I figure this out? Keep in your mind, I can say this right angle triangle. So this value will equal 22. So 80 minus 58. That makes sense? 80 minus 58. And this little value equal 63.5 minus 58 will be 5.5. If you assume this distance x, this little distance is x, and the whole distance is 0.01 minus 0.002. It will be 0.008. That makes sense? So I set up a right angle triangle from this relationship. The horizontal distance for this right angle triangle will be 0.01 minus 0.002 equal 0.008. The vertical distance, this one, equal 22, which is 80 minus 58. So I can set up a triangle similarity. So I have this right angle triangle. This value equal 5.5. This value equal 22. This distance, I assumed it x. And the whole distance equal 0.008. So I can say 5.5 divided by 22 equal x divided by 0.008. What I did, I made a triangle similarity between this triangle and the bigger one, this one. So I can figure out the distance x from this relationship. So 5.5 times 0.008 divided by 22, this value equal 0.002. So if this distance x equal 0.002, the corresponding strain here will be 0.004. Because this distance is 0.002, and we need to add another distance x, which is 0.002. So the corresponding strain here will be 0.004, which is corresponding to the applied stress 63.5. So for this stress, we will have a strain, corresponding strain equal 0.004. Does that make sense? Keep in your mind, any strain equal the elongation in this wire divided by the original length. Since the corresponding strain in member AB or wire AB equal 0.004, and the original length of wire AB equal 2 feet, I will multiply it by 12 to be an inch. Then I can figure out what is the expected elongation in this member. So the expected elongation in member or wire AB will equal 0.096 inch. Let me repeat it one more time, but for member BC. We have another member BC or wire BC. The force in wire BC equal, what was the force in wire BC? 10,098.1 pound. The diameter of wire BC equal 3/16 inch. So the stress in wire BC will equal the force 1098.1 pound divided by the cross-section area by divide 4 times diameter square. So the stress equal 39,769.4 psi. I will divide it by 1,000 to be 39.8 psi. So the stress is 39.8. 39.8, that means you are around here. 39.8. What will be the corresponding strain? What will be the corresponding strain? It's very easy to figure out the slope of this linear relationship. So right now, we have this linear relationship. Here is strain, here is stress, and we have the value here equal, I think, 58. And the corresponding strain here equal 0.002. Is that correct? Yes. So right now, we have a level of 39.8 stress. What will be the corresponding strain? It's very easy. The slope of this linear relationship equal 58 divided by 0.002. This slope using this point must be the same slope using this point, which equal 39.8 divided by the epsilon, the corresponding strain. I can figure out the corresponding strain in member BC will equal 0.00137. So the strain in member BC equal the elongation in this member divided by the original length of this member. So 0.00137 equal the corresponding elongation divided by the original length. The original length of this member was 3 feet. I'm gonna multiply it by 12 to be an inch. So the elongation in this member will equal 0.05 inch. That makes sense? So this example is a very good example. We need to figure out what is the expected elongation in the wires BA and BC. So we have to start first with the engineering mechanics bar to figure out what are the internal forces in these wires. Once you get the internal forces, I can figure out the stress by dividing this force by the cross-section area to find the stress. Then I'm gonna use this given stress-strain relationship with the stress. Then I can figure out the strain. Once you get the strain, this strain equal the elongation divided by the original length, then I can figure out the elongation. We can judge the behavior of the material based on the stress-strain relationship for this material. The material can be ductile material and it can be brittle material. We don't like brittle material. We like ductile material. Ductile material is a material with large deformations at failure. If you look to this stress-strain relationship, we have after yielding or after the linear relationship or the elastic stage or the elastic region, we have more deformation, more strain. This more strain is a reflection for more or large deformation. Also, this ductile material for steel and equal in tension and compression. If you have a ductile material, this ductile material will give you warning before failure. If you remember, after we reach to the highest level of stress, which is the maximum or the ultimate stress, after this level, we have necking. The cross section will be reduced at a local position. This necking in the cross section will give you indication that failure is coming. So we have warning. However, for brittle material, after you finish up the linear relationship and start the plastic deformation, failure suddenly will happen without large deformation, just a little bit. No deformation at failure, little or no. Like bricks, stone, glasses. No warning, no visual warning. We cannot see any indication that failure is coming. That makes sense? So one of the applications of stress-strain relationships, we can judge the type of the material. Is it ductile material? Is it brittle material? Based on how much deformation do you have after the linear or the elastic region. Another parameter which is very important, I would like to explain it here first, then I will introduce it. If you have a member, this member under tension, force F, we decided that during the tension test, the length of this member will be stretched. At the same time, the diameter of this member will be reduced. So we have elongation in the same direction of the force, and we have contraction in the opposite direction. If you divide what happened in the lateral direction and what happened in the longitudinal direction, this is called Poisson ratio. Poisson ratio, which is called nu, is the ratio between the lateral strain, what happened in the lateral direction, to what happened to the longitudinal direction. So the ratio between the lateral strain to the longitudinal strain. Nu equal epsilon lateral divided by epsilon longitudinal. The Poisson effect, the deformation, expansion, or contraction of a material in direction perpendicular to the specific direction of loading. Keep in your mind, what happened under tension will be the same if you have a member under compression. If you have a member under compression, yes, we will have contraction. The length of the member will decrease, but at the same time, the diameter will increase. So if you divided the new deformation by the original length, you can get a strain. So we have longitudinal strain. Longitudinal means in the same direction of the applied force. And we have lateral strain. Lateral means in the direction perpendicular to the direction of loading. If you divide the lateral strain by the longitudinal strain, we can get the value of Poisson ratio. That makes sense? So we have two examples here for Poisson ratio. We have a rod with a length equal 100 millimeter and a diameter equal 15 millimeters. So this rod with a diameter equal 15 millimeter and original length L naught equal 100 millimeter. And this rod is under the effect of tension force equal 10 kilonewton. And this force will apply stress in the elastic range. We need to figure out what will be the change in the diameter. That's fine. Keep in your mind, this force, if you divide this force by the cross-section area, you will get the stress in the rod. So this stress will equal the applied force 10 kilonewton. I will multiply it by 1000 to be in Newton and divided it by the area of the cross section by divide 4 times diameter 15 square. Then I can figure out the stress in this member 10 times 1000 divided by divide 4 times 15 square. So the stress will be 56.59 megapascal, because this one will be Newton per millimeter square, which is megapascal. Keep in your mind, we have a relationship between stress and strain using Hooke the law. Your stress equal Young's modulus E time strain. Stress in this rod is calculated 56.59. The Young's modulus of the material of this rod is given 70 gigapascal, so I'm gonna multiply it by 1000 to be in megapascal. Time strain. From this relationship, I can figure out the strain in this member or in this rod. The strain will equal 0.00081. This strain equal the elongation that will happen in the rod divided by, I'm sorry, wait. So this strain is called longitudinal strain. The strain in the same direction of the applied force. Keep in your mind your Poisson ratio, which is given, nu, equal the ratio between the lateral strain divided by the longitudinal strain. So the Poisson ratio is given for this material, it's 0.35. The longitudinal strain, you calculated it, 0.00081. So I can figure out the lateral strain. Lateral strain in the direction perpendicular to the applied force, laterally. So the lateral strain will be 0.00028. Keep in your mind, this lateral strain equal the change in the diameter divided by the original diameter of the rod. So this one is the change in diameter divided by the original diameter. So the lateral strain equal 0.00028. The change in diameter, I don't know. The original diameter of this member was 15 millimeter. So I can figure out what will be the change in the diameter. It will be 0.0042 millimeter. So we have a change in the diameter, looks like reduction in the diameter. So keep in your mind, this is the rod, and we have applied force here F, and another applied force here F. This member will be stretched like this. At the same time, the diameter will be reduced by 0.0042. This is the change in the diameter. That makes sense? So determine the change in its diameter. The diameter was 15 millimeter. We will have reduction in this diameter by 0.0042 millimeter using the Poisson ratio parameter. That makes sense? We have another example here. We have a bar with rectangular cross section, 100 millimeter width and 50 millimeter thickness, and the total length is 1.5 meter. This rod or this bar made from steel A36 with Young's modulus equal 70 gigapascal and the Poisson ratio 0.35. And the applied force equal 80 kilonewton. We need to figure out what are the changes in the length and the change in the dimensions of its cross section. The total length of this bar will be changed, and the cross section dimensions 100 millimeter and 50 millimeter will be changed. How much? So first step, the stress in this bar equal the applied force 80 kilonewton. I'm gonna multiply it by 1000 to be in Newton, divided by the cross section area of this bar, which is 100 times 50. So the stress will be megapascal, 80,000 divided by 100 times 50. I got 16 megapascal. We using Hooke the law, in stress equal Young's modulus times strain. So the stress equals 16 megapascal, Young's modulus equals 70 gigapascal. I'm gonna multiply it by 1000 to be in megapascal time strain. So from Hooke the law, I can figure out what is the expected strain in this bar. Equal 0.00228. Keep in your mind, this is the longitudinal strain in the same direction of the applied force in this direction. This strain equal the elongation in the bar divided by the original length. So the strain is 0.00228 equal the elongation in this bar. I don't know. The original length of this bar is 1.5 meter. I'm gonna multiply it by 1000 to be in millimeter. So I can figure out the elongation of this bar. It will be 0.34 millimeter. This is the change in the length of the bar. We have a change in the length. Keep in your mind, your epsilon, your nu, which is Poisson ratio, equal lateral strain divided by longitudinal strain. So Poisson ratio is given 0.35. Lateral strain is unknown. Longitudinal strain is 0.00228. So I can figure out the lateral strain will equal 0.00079. So the lateral strain equal 0.00079. Keep in your mind, this lateral strain equal the change in the width divided by the original width. Or this lateral strain equal the change in the thickness divided by the original thickness. Here is the bar. It was like this. This width equal 100 millimeter. The thickness equal 50 millimeter. And this is the length of the bar. That makes sense? So the lateral strain represent what is the change in this width? Change in this width divided by the original width. So this lateral strain 0.00079. The original width was 100. So I can tell you what will be the change in the width. The change in the width will be 0.0079 millimeter. This lateral strain 0.00079. This original thickness was 50 millimeter. So I can tell you what will be the change in the thickness equal 0.00395 millimeter. So any change in the cross section will be measured by the lateral strain. This lateral strain can be calculated from the Poisson ratio, which equals the lateral strain divided by the longitudinal strain. This longitudinal strain can be figured out from the Hooke-the law. If you can figure out the stress and you have Young's modulus, I can figure out the longitudinal strain.